Welcome, architects and developers, to our deep dive into building resilient systems. If you've ever felt the drag of a monolithic codebase or yearned for more agility in your deployments, you're in the right place. Today, we're cutting through the buzzwords to lay down a precise, actionable definition of microservices and their core architectural principles. Think of it like this. Instead of building a single, giant, unbreakable block of software, we're assembling intricate systems from advanced Lego bricks. Each microservice is one of these bricks, a small, autonomous piece, responsible for a single business capability. And critically, it's designed to be self-contained and independently deployable. This isn't just about smallness. It's about a fundamental shift in how we approach domain modeling, emphasizing what we call bounded contexts to carve out clear, undeniable ownership. This architectural philosophy allows teams to iterate rapidly on their specific brick without impacting the entire structure. You might be thinking, but how does that translate into practice? Well, it means each service maintains its own lifecycle, from development to testing and deployment, completely independent of others. In real systems, this shows up when a bug fix or a new feature in, say, your inventory management service doesn't require a full rebuild and redeploy of your user authentication or order processing services. This autonomy extends to data management too. Each microservice owns its data store, ensuring true isolation and preventing unintended side effects across service boundaries. No more shared databases turning into a tangled web of dependencies. Instead, we embrace decentralized data management, allowing each brick to optimize its persistence layer for its specific needs. Ultimately, a well-architected microservice system is a collection of loosely coupled, highly cohesive services, each communicating via well-defined APIs. This approach fundamentally improves fault isolation. If one brick fails, the entire structure doesn't collapse. It also unlocks unprecedented scalability and allows for technology diversity, letting teams pick the right tool for each job. Understanding these foundational principles isn't just academic. It's the bedrock for truly resilient, evolvable software systems. But every powerful tool has its trade-offs. So, next, let's critically examine how microservices stack up against their monolithic counterparts. Alright, so in our last session, we decoded microservices, understanding their core principles. Now, let's get into the why. The critical trade-offs that truly drive architectural decisions for us developers. We can't just jump to microservices without truly appreciating what we're moving from, right? Often, that starting point is the venerable monolith. Think of a monolith as that single, giant block you could try to build an entire structure with. All your code, all your features, bundled together in one deployable unit. It's often the easiest way to start a new project, especially for small teams or startups. Initial development is fast, debugging is straightforward because everything lives in the same process, and deploying means pushing just one artifact. There's a comforting simplicity to that unified structure, isn't there? Everything is local, everything is interconnected by default, but that simplicity, as we'll see, comes with its own set of scaling pains. Now, contrast that with microservices, our advanced Lego bricks. Each service, like a self-contained Lego piece, is designed for a single, well-defined purpose, operating independently. The benefits for us, the developers, are compelling. For one, language diversity. No more forced tech stack lock-in. Your recommendation service can be in Go, your user profile in Node, JS, your payments in Java. You pick the best tool for the job. More critically, there's fault isolation. If one service crashes, it doesn't take down the entire application. Imagine if a minor glitch in your user preferences brick brought down the entire house. Unacceptable, right? With microservices, that single brick fails, but the rest of the structure remains stable. This independent nature also extends to scaling. You only need to scale the bottlenecked service, not the entire application. You might be thinking, this sounds too good to be true, what's the catch? In real systems, this shows up when teams face legacy monoliths, where even minor updates take weeks to test and deploy due to complex dependencies. Breaking it into smaller, independently deployable services transforms that bottleneck into a stream of continuous, low-risk deployments. It's about enabling individual bricks to be swapped or upgraded independently, without impacting the whole, But here's where the pragmatic developer's skepticism kicks in, and rightly so. That independence comes at a cost. Distributed systems are inherently complex. Suddenly, instead of local method calls, you have network calls. This introduces operational overhead. Managing dozens or hundreds of services, their deployments, their logging, their monitoring, their security. It's a completely different beast than managing a single artifact. Then there's data consistency. In a monolith, a single database transaction guarantees atomicity. In microservices, achieving consistency across disparate data stores often requires eventual consistency patterns, which means embracing a different mental model for data integrity. And let's not forget distributed debugging. Tracking a request through multiple services, potentially across different languages and infrastructure, can be a nightmare. Network latency, serialization issues, service discovery. These become your problems. So while microservices offer incredible agility and resilience when done right, they also introduce a significant distributed systems tax that demands careful planning and robust tooling. Understanding these trade-offs is crucial because next, we'll talk about when microservices actually solve core technical challenges, and crucially, when they absolutely do not. After diving into the high-level trade-offs, let's get down to the brass tacks. What specific technical headaches do microservices actually solve? You might be thinking, my current codebase feels like a tangled mess. Or maybe scaling one tiny part means scaling everything. And you'd be right to feel that way. Microservices shine when your monolithic architecture starts to buckle under its own weight. We're talking about that crippling codebase complexity that grinds development to a halt, the tech stack lock-in that prevents you from adopting newer, more efficient tools, or the inability to scale specific, high-demand components without over-provisioning resources for the entire application. These are the kinds of problems where a microservice approach, like building with advanced Lego bricks, lets you swap out a single, outdated brick without rebuilding the entire structure. Each service becomes a self-contained, independently upgradable piece of your system. In real systems, this shows up when a single customer-facing API or a back-end payment processor becomes a bottleneck. Instead of trying to optimize a giant monolith that handles every single domain, microservices let you isolate that bottleneck into its own service, scaling just that piece. This brings fault isolation too. If one brick breaks, the entire Lego castle doesn't collapse. However, it's not a silver bullet. Jumping into microservices too early, or for a small team, can be detrimental. The operational overhead, the complexity of distributed systems, and managing data consistency across many services can turn your elegant Lego castle into a logistical nightmare if you don't have the right processes and tools in place. It's about knowing when to choose those specialized bricks, not just having them. So with these core problems and their solutions in mind, what technologies and patterns do we actually use to build these resilient microservice systems? That's what we'll explore next. Now that we've understood why microservices can be a powerful choice, let's dive into the how. Building these resilient systems, much like assembling those advanced Lego bricks, requires specific tools and established blueprints to ensure everything connects and interacts reliably. First, we need the foundational technologies that make microservices deployable and manageable. Think of Docker and Kubernetes as your advanced packaging and orchestration system. Docker lets you containerize each service, ensuring it runs consistently across environments, just like each Lego brick is self-contained. Then, Kubernetes becomes the intelligent platform that manages these containers, ensuring your services are always running, scaling, and resilient. For communication, RST and gRPC are your primary protocols. RST, with its simple HTTP verbs, is great for general-purpose requests, while gRPC offers high-performance, contract-first communication, especially useful for internal service-to-service interactions where efficiency is paramount. These are the advanced connection pieces that define how your bricks talk to each other. Next, as your system grows, you'll encounter challenges in data flow and inter-service communication management. This is where tools like Apache Kafka shine. Kafka provides a robust, distributed streaming platform for asynchronous messaging, allowing services to communicate without direct coupling, creating a more resilient data pipeline. You might be thinking, This sounds like a lot to manage, especially with numerous services communicating. This is precisely why service meshes like Istio or Linkerd become indispensable. In real systems, this shows up when you need consistent traffic management, security, and observability across all your microservices without embedding that logic into each service's codebase. A service mesh essentially layers a communication infrastructure over your services, handling things like circuit breaking, retries, and metrics collection automatically. Finally, beyond the technologies, we have crucial architectural patterns that act as the blueprints for solving common distributed system problems. For managing distributed transactions, the Saga pattern allows you to maintain data consistency across multiple services when migrating a monolithic application to microservices. The Strangler Fig pattern provides a structured way to refactor piece by piece, gradually replacing old functionality. The API Gateway pattern offers a single entry point for clients, routing requests to the appropriate services, and handling cross-cutting concerns like authentication. And for protecting your system from cascading failures, the Circuit Breaker pattern is essential, preventing a failing service from bringing down others by quickly failing requests and providing a fallback. These patterns are your architectural toolkit, helping you build truly stable and resilient Lego structures, even when some individual bricks might falter. Understanding these technologies and patterns is crucial, but knowing how to apply them effectively is where true mastery lies. So how do we integrate these concepts into our daily development workflow? That's what we'll explore next. Best practices for designing, developing, and testing microservices effectively. Alright, we've explored the technologies and patterns. Now let's talk about the how. The foundational practices that turn potential chaos into a well-oiled, resilient microservices system. It's about how we design, develop, and ensure the quality of each of those advanced Lego bricks. First up, we need to talk about domain-driven design, or DDD. Think of DDD as defining the precise purpose and boundaries of each of your microservice Lego bricks. It's about creating bounded contexts. Clear, explicit lines that prevent services from becoming entangled monoliths in disguise. For developers, this means understanding the core business domain that each service owns, and then meticulously defining its public face, the API contracts. These aren't just endpoints, they're the stable, versioned interfaces that other services, or even external consumers, rely on. Without robust, immutable-by-design contracts, you're not building a sturdy Lego structure. You're just stacking wobbly blocks, hoping they don't fall apart. Now, with independent bricks, you might be thinking, how do I manage data across all these services? This brings us to data consistency strategies. In a distributed system, immediate, strong consistency across all services is often a performance killer. This is where eventual consistency becomes your pragmatic friend. It acknowledges that data might take a moment to propagate across services, but it will eventually be consistent. This requires careful design, often leveraging event-driven architectures. I've seen teams wrestle with complex distributed transactions that try to mimic monolithic ACID properties, only to realize they've introduced more coupling and fragility. Instead, embracing eventual consistency with mechanisms like the Saga pattern can empower services to remain autonomous while ensuring overall data integrity over time. Crucial to validating all this is effective testing. We're talking unit tests, integration tests that verify API contracts, and end-to-end tests that simulate user journeys across multiple services. It's like thoroughly shaking your Lego model to ensure all the connections hold, even the ones you can't immediately see. Finally, no resilient system is truly resilient without being secure and observable. Securing microservices isn't an afterthought. It's baked in from the start. This means implementing robust authentication and authorization, often at an API gateway level, and securing inter-service communication with mechanisms like mutual TLS, MTLS. Managing secrets and sensitive configuration must be centralized and automated. Beyond security, operational excellence is paramount. Comprehensive logging, tracing across service boundaries, and real-time monitoring are your eyes and ears into a distributed system. They provide the signals that let you quickly identify and resolve issues before they escalate. After all, what truly differentiates a well-architected microservice from a tangled mess? We'll dive into those technical differentiators next. After mastering best practices, it's time to talk about the concrete, measurable advantages a truly well-architected microservice system brings to the table. These aren't just buzzwords. They translate directly into tangible benefits for your team and your product. First up, let's talk about why microservices drastically improve system resilience and reliability. Think back to our Lego analogy. If one brick in your giant monolithic structure fails, the whole thing could come tumbling down, right? With microservices, that single faulty brick, that isolated service, can fail without taking down the entire application. You might be thinking, how does this really prevent downtime in practice? Well, it's about fault isolation. Each service runs independently. If your recommendation engine has a memory leak, only that service goes down, not your entire e-commerce checkout. You can gracefully degrade, perhaps showing static recommendations, while the faulty service is detected, restarted, or even replaced, leading to significantly faster recovery times. This inherent isolation also unlocks immense potential for optimized scalability. We often need to scale specific parts of an application more than others. In real systems, this shows up when you have an e-commerce platform that experiences a massive spike in traffic only on its product browsing service during a flash sale. Instead of over-provisioning resources for the entire monolithic application, you can scale just that product browsing microservice to handle the load, saving significant infrastructure costs. This isn't just about scaling up, it's also about scaling efficiently, even horizontally, leveraging polyglot persistence and programming languages where they make the most sense for a specific service's performance needs. That focused resource allocation ensures your budget goes further and your hot paths stay blazing fast. Finally, and this is huge for us developers, microservices accelerate deployment capabilities and dramatically improve maintainability. Smaller, focused codebases mean less cognitive load. Onboarding a new developer to a single microservice is far simpler than dropping them into a million-line monolith. You're deploying small, independent changes, reducing the risk of a widespread regression. This enables more frequent, faster releases, getting features and bug fixes out the door in minutes, not days or weeks. It's about reducing friction, empowering smaller teams to own their service end-to-end, and fostering a culture of rapid iteration. But how do these advantages play out in specific, real-world development scenarios? Let's dive into some hands-on examples next. You've likely faced the daunting task of navigating a sprawling legacy monolith. Imagine trying to upgrade one tiny, crucial component, but you have to rebuild the entire house just to replace a single brick. That's the first real-world problem microservices tackle: refactoring a monolithic codebase. These systems often suffer from overwhelming complexity, making changes slow, risky, and deployments a high-stakes gamble. Microservices, using patterns like the Strangler fig, allow you to incrementally peel off functionality, one service at a time, gradually transforming that giant block into a more manageable, modular structure. Then there's the challenge of building new features into an existing, often aged, system. You might be looking at your own codebase right now, thinking, how do I introduce this cool new tech without rewriting everything? Trying to shoehorn a cutting-edge recommendation engine into a decade-old Java monolith, for instance, is not just difficult, it's often impossible without compromise. This is where microservices shine. Acting like those advanced Lego bricks we talked about, you can build that new feature as an entirely new, independent service, using the best fit technology, without disturbing the core. I've seen teams slash development time by focusing on just that new brick, ensuring it integrates cleanly without touching the rest of the topology structure. Another common pain point? Optimizing a performance bottleneck. Picture a critical e-commerce system where the payment processing module suddenly becomes a massive resource hog, slowing down everything from user authentication to product catalog browsing. In a monolith, scaling up means scaling everything, which is incredibly inefficient and costly. With a microservice architecture, you identify that specific bottleneck, that one struggling brick, and isolate it. You can then scale only that payment service independently, perhaps even optimizing it with a different programming language or database better suited for its specific demands, without affecting any other part of your application. These aren't abstract problems. They're the daily realities developers and architects face. Microservices offer tangible architectural solutions to these challenges, enabling faster delivery, improved resilience, and more focused development. But as with any powerful tool, they introduce their own complexities. Understanding when and how to wield them is critical, because while we gain immense flexibility, we also enter the realm of distributed systems. Alright. Alright, so we've spent a lot of time talking about the power of microservices, how they're like advanced Lego bricks, each self-contained and independently swappable. But even with Lego, if you don't understand how they connect and interact, that stable structure can become surprisingly fragile. And in distributed systems, those complexities can manifest as some real head-scratchers for developers. First up, let's tackle the operational vortex and the sheer agony of debugging across service boundaries. You might be staring at your logs thinking, which of these 15 services actually broke? Because when a request touches multiple independent bricks, pinpointing that single faulty connection or misbehaving service becomes a quest. The days of simply stepping through a single monolith with a debugger are long gone. This distributed choreography, while powerful, introduces a whole new layer of cognitive load and operational overhead that can truly grind development to a halt. In real systems, this shows up when you encounter issues like distributed transactions. How do you ensure data consistency across multiple, independent databases? We often turn to patterns like the Saga, breaking a long-running transaction into a sequence of local transactions. But even then, coordinating eventual consistency, handling rollbacks, and making sense of network partitions, where some services think another is down but it's not, can feel like wrestling an octopus. These aren't just theoretical problems. They hit you hard when you're trying to ship a feature or fix a production bug. But don't despair. Mitigation isn't just possible. It's essential. Robust observability tools like centralized logging, distributed tracing, and comprehensive metrics are your eyes and ears into this complex ecosystem. Designing smart API contracts with clear boundaries, implementing circuit breakers, and adopting thoughtful data consistency strategies, even if it's eventual, can prevent cascading failures. And for networking, using service meshes or intelligent API gateways helps abstract away much of that underlying complexity. It's about building resilience into each brick and the connections between them. Understanding these watchouts and their mitigations is absolutely crucial for any developer building with microservices. It's how you move from merely assembling bricks to truly engineering resilient systems. So, with these challenges in mind, are you ready to test your foundational understanding of microservices? Alright, we've navigated the complexities of microservices, from initial design to battling those tricky distributed system issues. You've seen the watchouts, the pitfalls, and the strategies to mitigate them. Now, it's time for a quick, technical competency check. Think of this as ensuring your understanding of how those independent Lego bricks, our services, truly manage their interactions. Here's a question that gets to the heart of a common microservices challenge. In a well-designed microservices architecture, what is the primary reason for avoiding traditional two-phase commit, 2PC, or distributed transactions for achieving consistency across multiple services? Option A. It significantly increases network latency and reduces overall system throughput. Option B. It makes independent deployment of services impossible due to tight coupling. Option C. It introduces a single point of failure and violates service autonomy, undermining resilience. And Option D. It requires specialized database software that is incompatible with cloud-native environments. Take a moment to consider which one truly captures the core architectural principle at play. Alright, the correct answer is C. It introduces a single point of failure and violates service autonomy, undermining resilience. While options A and B are certainly consequences of 2PC, the fundamental problem for microservices is how it undermines the very autonomy and resilience we're trying to achieve. Imagine trying to coordinate a single giant block rather than letting each Lego brick manage its own state and responsibilities. Each service, like a self-contained Lego brick, should be able to operate and recover independently. Forcing a distributed transaction means tying multiple services together into a single, atomic operation, creating a central coordinator, a choke point, and a single point of failure. This design directly opposes the core tenets of microservices: independent deployability, fault isolation, and autonomous teams. Instead, we lean into patterns like eventual consistency, sagas, and compensating transactions. You might be thinking, but how do I guarantee consistency then? That's where more advanced patterns come in. Managing the journey to consistency rather than insisting on instant, global atomicity. In real systems, this shows up when developers default to select for update across service boundaries, only to find their resilient architecture crumbling under the weight of distributed locks. Now that your brain is warmed up, let's explore your next architectural challenge together. Alright developers, we've journeyed through the intricate landscape of microservices. From breaking down monolithic, single giant block applications into advanced, interconnected Lego bricks, to managing their complex interactions and ensuring resilience. We've talked about when to use them, the patterns that make them robust, and the common pitfalls to avoid. But here's the real question that sparks debate in every architect's room, and one I'm truly to hear your thoughts on. What's the most challenging microservices boundary you've ever had to define or refactor? You might be thinking about that one service that just never seemed to fit neatly. Or the data consistency nightmare that kept you up at night. Sharing these war stories, these insights from the trenches, is how we collectively build a better understanding of resilient systems. So drop your experience, your architectural dilemmas, or even your aha moments in the comments below. I read them all, and I know the community will benefit from your perspective. If you found this deep dive valuable, or if it helped you connect some of those advanced Lego bricks in your own mental model, please hit that like button. Subscribe to Maven Developer and ring the notification bell so you don't miss our next explorations into enterprise-grade architecture. And for a comprehensive, hands-on guide, grab the full Microservices Architecture Playbook. The link is right there in the description.